Awesome. Thank you. Hi, everybody. I'm Paul Van Hagen. I'm Principal Bridge Engineer with Hardesty and Hanover here in London. I'm here to talk about the Henderson Colloquium that we recently had in Cambridge University in early July. It's a subject that's really close to my heart. I've been a moving bridge engineer pretty much on and off my whole career, about half of the time. And so I was involved in trying to coordinate and organize this event. Today, we're going to try to disseminate some information about what happened and recap and reprise some of the presentations that we made. We have three great panelists here. Simon Fryer of Buro Happold, who'll be talking about the complexities of temperature as it affects our designs. We'll have Ryan with BAM Nuttall talking about some of his construction experience and how that's led to the methodologies that he's using in a design and construction of a really interesting bridge in Northern Ireland and the Republic of Ireland. And Ezra, a good friend of mine from Moxon Architects, will talk about the art of moving bridges and the sort of dynamic environment that the bridges occupy from an architectural perspective. So some really interesting presentations to make. I'm just going to be up here for a few slides talking about the colloquium itself and the discussion themes that we went through during the colloquium, and just introduce sort of the environment that we all attended in a 3-day colloquium. And then we'll get into the panelists and their presentations, and then we'll have a chance to all kind of contribute at the end in a discussion session. So for those of you who don't know, that, and this actually was my first colloquium, they're held every year around the same time of the year. And they discuss the sort of the issues of the day in engineering. And we decided to look at this year the so-called intricate world of moving bridges. Sort of an exploration of all the sort of interdisciplinary nature, the very complex structures that involve design interdiscipline coordination, but also coordination with clients and usually with architects and certainly with constructors. So we wanted to kind of cultivate this interdisciplinary discussion and look at a way to kind of improve the practice in the United States and in the UK, and perhaps even potentially bringing it together. And so there are, as I said, it's an interdisciplinary, sort of design world that we're in. So we wanted to look at those and break those down, the structural, mechanical, electrical coordination, and how to bring all of those disciplines together to get a coordinated structure. And as I said, temperature movements is important to understand, and Simon will be talking about that in detail as we go on through this presentation. Early contractor involvement and supplier involvement. A lot of the elements that go into these structures are kind of off the shelf or have to be custom fabricated, and so getting that kind of advice from contractors is important. Of course, in the world that we're in today, sustainable practice needs to and ought to be accommodated within our designs, and we talked about that. There was one presentation about the sort of the pros and cons of counterweighting a structure, right? The real sort of heavy brute force perspective from a structural perspective, or non-counterweighted and moving that force into the machinery. There were attendees from the United States and from Britain and from Europe, all using different codes of practice. And there was a presentation on the comparison of those and juxtaposing those and looking at the pros and cons of those. We also need to talk about, skip to 7, the marine traffic and the involvement of the clients and the owners, the port authorities and the marine industry, and how to manage construction around the constraints. So as you can see, as we go through all of these items, it's a complex world, the kinds of things that one doesn't face in fixed bridges. The bespoke nature is important to recognize as well. Like there isn't I've been doing this 30 years. There hasn't been one moving bridge that's been, like the last. They're all custom fabricated, and yet they need to be reliable and operable, right? It's not like designing a car where you can upfront put in like years of research and development and then make many of them. This is just like one bespoke element that you have to get moving and operating reliably. So with all of those topics, it required like a diverse group of people, and here we all are. At Cambridge University, we stayed in the we stayed in the halls of residence, like sort of going back to the 80s for me. When I was in the halls of residence, we got to spend time together and each of us made a presentation on a topic that was close to our hearts, and we were able to kind of immerse into that environment within the university, talking and sort of communicating and sharing our experiences. And we'll talk a little bit later about how we can move that forward, taking those relationships and moving those forwards into an organized fashion to help, sort of further the practice. So there were 2 days worth of sessions. We arrived on a Monday night. There was a full day of sessions on Tuesday morning and afternoon. And then a morning session the next day on the Wednesday, and then a wrap-up session. And again, we'll have 3 of those sessions today with our attendees over here. I think that's sort of more or less what I want to get to. The panelists' assignment, as I said, I think I said this before, talking about temperature. Ryan will talk about his experience working on the Northern Spire and the Great Yarmouth Third Crossing, or the so-called Herring Bridge, and the Gullwing Bridge, which I know maybe a lot of you know about, since Arup was involved in that, and the Govan Partick bridges, and how those bridges came together to inform what he's currently doing. Really extraordinary presentation that was made there. And Ezra, we'll talk about it from the perspective of the architect. So I think that's it for me. If Simon could come up now. He'll be making the first panelist presentation. The heat is on for movable bridge design. Step back.
Good evening, everyone. So, as Paul mentioned, movable bridges give a lot of scope to come up with bespoke structures. These are a few of the ones that I've personally been involved in over the years. Some of them never got off the drawing board, unfortunately. Some of them probably shouldn't have got off the drawing board. But the one thing they all have in common is that they are quite unusual. They're all different to other projects. So with that in mind, I want to explore the approach that is taken to these very unique designs. And I'm going to use the topic of temperature effects to illustrate that. But I'm not just confining my comments to that. It's just quite an important subject. And I think you'll see from the project examples that I give how we've needed to go a little bit beyond what the standards say in order to verify how these structures will work. So I'll start by going into the temperature effects, illustrating that with reference to 2 case studies, projects that we've worked on, and then broaden out the discussion to designing from first principles and where perhaps the codes are not sufficient to give us all the tools that we need. And I'm hoping that at the end of the presentations, we can have a bit more of a discussion about this whole area. So I don't think I need to labour too much on why temperature effects on movable bridges might be important. There's plenty of press coverage of problems that have occurred, stories of the fire brigade coming out to douse down a bridge that has jammed in position. It's very important that we try to predict the thermal effects on a movable bridge. and make due allowance for that in its design. However, when you look into the basis of the thermal sections of the codes of practice, the Eurocodes, going back before that, the British standards, you find that it's based on quite a narrow amount of research. Actually, the original rules were based on some research done by the TRRL, the two reports that fed into the British standards, and that seems to have been perpetuated ever since in subsequent codes. And so there's a bit of a lack of research data in order to predict the effects of temperature on bridge structures. Now, with fixed bridges, that's obviously something that we would be interested in, but even more so with movable bridges, where we're not just trying to come up with a safe design, we're trying to predict how the structure is going to behave, and that's a little bit different. On the one hand, we want to make sure that joints are sized so that they won't jam, but equally, we don't want to be designing them so they're half a meter wide and they look awful. So we've got to try to get our predictions a bit more accurate. So a lot of you will be familiar with the Eurocode clauses for temperature. Tends to treat temperature effects in terms of uniform temperature change and then differential temperature change, which could be a linear or non-linear representation, depending on what kind of structure you've got. The emphasis is on vertical gradient through the structure. And you can see, if you can read the table, the maximum values of differential temperature get up to about 18 degrees. And this is not air temperature. This is structure temperature. You know, in the case of a steel bridge, this is the temperature of the actual steelwork. This is some measured data. On the vertical axis is delta T, so that's the differential temperature. On the horizontal axis is the ambient, or the average temperature of the steel in this case. And you can see there's a very strong correlation between the two temperature effects, which are treated by the code as being independent of one another. So that's one point. The second point is that actually you're getting up quite a lot higher than 18 degrees with the differential temperature effect, according to this graph. So let's look at a couple of case studies. First bridge I want to consider is the Little Langebro in Copenhagen. Some of you may know the structure. It's got a very complex geometry. Its main members are formed by doubly curved triangular box sections along each edge of the structure, which are exposed to the elements completely. This little animation shows the variation of the cross-section as you go from one end of the bridge to the other. And it's meant to replicate the flapping of the wings of a bird. Not only does it have that complication to its geometry, it also has planned curvature. So how do we predict the temperature effects on a bridge like this? How do we start a video? Okay, this video is supposed to show how the bridge opens, but the two central portions of the bridge is divided into four. The two central portions of the bridge rotate. One moves slightly before the other. And they come together with a joint which is obliquely cut across the bridge decks. So the point of showing this is just to emphasize the importance of accurately predicting the thermal effects on this structure. Oh, there we go. All right, there we go. I'll know the next time. So there we go. This is a clause in the Eurocode which deals with horizontal temperature difference. So the previous clauses are primarily about vertical temperature gradient. But you can imagine with a structure like that, where horizontal curvature is in play, there's all sorts of twisting and geometric changes going on. You'd also want to consider what happens across the width of the structure. Now, the Eurocode does say that you can determine that from first principles, but the default is that a 5-degree temperature difference is used. But that bridge is essentially, the alignment of the bridge is north-south, so you have east on one side, west on the other. Over the course of the day, one side is going to be affected by the sun, and then the other side affected in the other way. So this is a little bit deficient in terms of being able to predict the behavior of the bridge. So how do we tackle this? This is our shell model for the bridge. So every plate was explicitly modeled in the bridge. And what we did was we used a Rhino model, and we analyzed the path of the sun at every time of day or every time of year in order to create an envelope of the effect of the sun on the plates of the bridge. And then we applied loading to the structure. I think it was a 12-degree temperature rise to plates that were affected by the sun at any given time. And you can see from the pattern of the sun loading that gave some very interesting effects on the structure. And this is the resultant movement ranges that were calculated at the joints. So that bridge was constructed and has behaved well, but we now have another challenge. This is the Royal Victoria Dock Bridge at Silvertown, which again has a quite complicated geometry. It doesn't have the doubly curved twisted structural members, but it does have an interesting plan geometry. That's the nature of the structure itself. And this is how it opens. So it's a double leaf bascule, but the two opening leaves are such that the outer radius is on opposite sides. So if you can imagine, the temperature effect tends to affect each of those leaves in the opposite direction, which gives some interesting concerns, potentially. So again, we wanted to be extra sure about the way that we predicted the thermal movements on this bridge. So we went one step beyond what we'd done with the Little Langebro, and we used some clever software, some scripting, a plugin to Rhino called Ladybug, weather data from the adjacent London City Airport. And this time, rather than just applying a temperature rise to the plates affected by the sun, we actually looked at the irradiance that those plates experienced. And that can be related to the heat that they gain and therefore the temperature rise. And so it was a much more sophisticated bit of analysis. we were taking account of the time that each of the plates was heated. So again, this bridge runs north-south, and so similar sort of sun path to the other bridge. And you can see how that can be put into an analysis model, and we can get an envelope of all the movements. So it's a bit of a brute force way of doing it by computational power, basically, but it's a possibility that's open to us now, whereas it wouldn't have been in the past. And this is all in addition to doing the codified checks, by the way. So we don't ignore the code. We do the code checks as well, but this is an additional check, which we deem to be sensible. These are longitudinal movements at the joints that have been calculated. When the opening leaves come together, there are pins that lock them. But if the bridge is just closed, then obviously there's a possibility for misalignment, and those pins need to be designed to cater for that misalignment. So that's another factor to be considered. Okay, so hopefully you can see the sort of thing that we've got into to try to think outside of just what's in the codes when we're designing these structures. So I've started with a blank sheet of paper here. And I'd like to just make the point that although the codes and standards are not there to be ignored, they only go so far. There isn't a standard which relates specifically to a lot of these structures. In fact, we know that the codes and standards which relate to movable bridges in general are potentially need to be bolstered a bit. So we now have this computational power, and personally, I'm not an expert in this at all, but we do have some very, very clever people who are able to write scripts, and we can just look at every conceivable possibility and envelope the whole lot, and then just gain the confidence that we've done that process, and we're not trying to second guess exactly how these structures are going to behave. So I've given the example of temperature, but there could be other things that we might think about. I mean, maybe probabilistic design of loading patterns and so on could be something that we look into, and that might lead to savings in terms of material use. And then the last point is actually, if you looked at the figures for what we designed for in terms of gaps on the Copenhagen Bridge, you will have seen that we didn't just work to 37.56 millimeters. We allow for construction tolerance, and there's always a need to be practical about these things and use some engineering judgment. Hey, thank you very much.
Good evening, and thanks for having me. My name's Ryan Dillon. I'm an engineering manager with BAM, UK and I now, so BAM Ireland at the minute, so that's not strictly correct. I guess Paul talked about the themes of the colloquium, and what I tried to touch on was really the interdisciplinary challenges that structures of this complexity pose, and how that respect and mutual differences and working together is completely fundamental and essential to success. And I guess the other theme being a contractor, the importance of early contractor involvement, and how our methods can have beneficial effects for our consultant, architect, and our client teams. So without further ado, how a swan, herring, seagull, and a tall ship have made the narrow water bridge possible in Ireland. So the narrow water bridge is a €103 million signature crossing connecting the north and south of Ireland. We have two spans, 138 metre clear span to the intermediate pier, which is on the left side of the picture is the south side of Ireland. It's asymmetric pylons on our southern side with a 90 metre inclined pylon with 8 pairs of cable stays. And on the northern side, we have a 57-metre clear span rolling bascule with a hybrid counterweight above and below deck. So it's a signature project also of the Shared Island Fund and a sign of what a new Ireland could be, and hence the significance of its location. So geographically, we're crossing the narrow stretch of river between the north and south of Ireland, and it's also a site of a standing natural beauty in that you've got Carningford Loch, which is an SAC. You've got the Mourne Mountains to the north in County Down, the Coolney Mountains to the south in County Louth, and the Ring of Gullion in County Armagh and Down. So you're connecting 3 years of outstanding natural beauty across a sensitive watercourse and a particularly contentious stretch of water. So it's been used for many years for nefarious purposes, smuggling poaching across the border and things like that. But also you can see Narwater Keep here in each of these pictures and the significance of that. And hence, this is probably the most expensive way to cross that particular stretch of water, but it's a beacon, I think, for what a modern Ireland could be. And I do this again, boys. And my phone's ringing. Case can go away. So there would be a more efficient way of crossing this without doubt. But what they're trying to do here is stimulate economic growth and tourism in what is a beautiful part of our country, where the White Atlantic Way in the west has stimulated growth there, the east feeling left out, and Narwater is going to be the beacon for that. It's also the site of the most significant loss of a British soldier's life and their troubles, where 18 were blew up, and this event stimulated discussion between civic leaders north and south of the border. We can do better. How can we come together? And 50 years later, and 25, well, maybe 30 now, after a peace process, and being a child of the peace process, it means a lot to be part of what Narwater's going to bring. So that's in the past. Let's move on. Our proposed construction site was presented and consulted on was what you would generally see in that, say, 200-ton sections prefabricated and spliced on site over temporary works, increasingly working out sequentially from our south abutment, and the same for the bascule span on the northern side. Doable, but if we look past and the experiences of Mr. Calatrava, both in Seville and California, these structures are costly, they overrun, and they present quality issues, and they get done and they are beacons, but both of those schemes, while beautiful, overrun on both budget and time, and the first thing we said is we're not doing that here. So in swims our swan. Our swan in the story is the Northern Spire in Sunderland. A good friend Simon was involved in it. So I once thought I was a maritime engineer, and then I got a chance to build this, and I fell in love with bridges. And Simon and friends looked after the deck, but I looked after the pylons, so I'm going to talk about it. I see what crystallised it, not unlike Narwater. So Narwater was shelved 10 years ago because of budget constraints, and it was deemed not to be buildable. Northern Spire was the same, and it took a bit of clever engineering and interdisciplinary coordination to get that over the line. And those are crystallised in the erection of our pylon, which was a 110-metre high, 1,600-ton composite structure, prefabricated in Belgium, one piece, floated across the English Channel, up a similarly tidally challenging watercourse, and erected on site, 100 metres off the shore. While this isn't a moving structure, it was without doubt a challenging one, and it needed that interdisciplinary coordination between our architect, our consulting engineer, the main contracting team, which I was part of, and our specialist supply chain, being Sarns and Victor Boyk. And without that, it would not have been a success, but it was a resounding success, and what a job it has been. But also, bridge building's a sort of closet industry, and that the relationships you build tend to resurface again a few years later. And a lot of the key relationships formed in this project have now come together to make Narwater possible, albeit via different employers. In swims our herring, the silver darling of the East Coast. The herring in this story is Great Yarmouth Third River Crossing, and I've used it a few times to dispel a few red herrings in the industry, particularly Mr. Farmer and the Farmer report that we must modernise our day and do things deliberately differently. I think we're doing just okay. This is an example of how design and construction teams, innovation, collaboration, and integration alongside a well-aligned client team, can form a sweet spot where the project goals are met, it's delivered on time, on budget, and it serves the community it's intended to. So Herring Bridge in Great Yarmouth, we had a very well-informed client that knew what he wanted. He wanted a bridge that could open 15 times a day without fail, without giving challenges. So we were splitting the Light Riverport in half. And again, that similar environment that we had in Northern Spire come together again, this time on the JV. And again, brave concept, well executed. And this one obviously opened earlier on in the year to success, and it's opening well. The key decision that informed Great Yarmouth was selection of bridge form. We were £7 million cheaper in our competition and 9 months quicker in programme. A lot of that's down to the bridge form we selected. So we had a Hardesty and Hanover in one corner, bringing the moving bridge experience, ROD on the structural end, and a contracting team that wanted to wrestle their way through solving a problem. The defining decision was to go with a below deck balanced counterweight structure with a very efficient mica system. That was made possible via piling through an existing quayside, which was dilapidated and fallen over. Our competition was scared of that and stayed away from it, and as a result, they had a huge counterweight, which pushed up their price. We then took the decision to optimise or rationalise our temporary and permanent works by combining them and then using them in the permanent case. So once we put on our combi wall, we then used that in the permanent case, giving us a lovely, deep, wide bascule chamber, just like a lovely balanced counterweight and a nice, efficient operating system, which you'll see a nice animation of now from Paul and the gang at Hardesty and Hanover. And I had the pleasure of being there yesterday and took a few colleagues inside it, and it's nice to see it performing as well as it is. Turn your phones off, folks. So that's Great Yarmouth operating. And Swip's the noisy neighbour, and I'm conscious I'm in IABSE office here. So we're Gullwing and Lowestoft. So we're in a JV, and I was with my former employer Farns at the time, sitting alongside our BAM colleagues that were currently doing an ECA contract for the Gullwing, or the third Lake Loading Third River Crossing, it was called at that time. Heard various noises of how things were going, and was impressed at the technical marvel that they were trying to embark on. And then got a phone call one day to come back into the office. It was back up in the market as a tender. And I was like, what? And was then told to go and try and price it from BAM's grasps. That we did for the same price as BAM. And I know you guys designed this here and you've done a good job, but this is an example of how a poorly aligned client and partner, the relationship can break down and ultimately end in a perfect storm here where you have a well-delivered, beautiful structure that moves and performs as it should, but it costs more, overrun, and a lot of that. And Connor did a very good presentation that gave me the backstory to how this happened. So if we look at the DCO approval in Great Yarmouth, Norfolk didn't go for DCO till they had our partner on board. So we got to rewrite the DCO to suit the methods that we needed, and changed piling methods and changed limits of deviation and everything. And that was written into the DCO. So then we had carte blanche to go and deliver that scheme. So starting 6 or 8 months after Lowestoft, we finished quite a bit in front of it and delivered on time, on budget. Where Suffolk were dealing with politicians and budgets and press on. And was it Monsall at the time? No, it wasn't. WSP's predecessor now. Pushed through the DCO and those applications. Then ARAP and BAM had to jump through several hoops to try and build it within the limits of the deviation and what the constraints were. And then they couldn't get agreement at the end of their ECA. And then went back out to tender and spent 9 months competing again. And then that delay pushes you into COVID and an option A contract. And my former employer wins it. And then we hit COVID and hyperinflation. And everybody involved in the scheme was taking pain. And all of that is out of those relationships and probably having another well enough informed client making decisions that they probably weren't informed to make. Look, the scheme is built, well done, ARAP, but everybody's at a bit of pain. And the lack of route from a contracting team to your design team, which I'm sure you guys are answering queries of ways we find trying to build that, is it couldn't be two more contrasting schemes 30 minutes apart as an example of how important a well-aligned client contract and consulting team should be to deliver structures of this complexity. Then comes our tall ship, which is the Govan Partick Bridge, which had a very similar proposed construction sequence as what I shown in our water at the start. And we were brave enough at the time to say that's not what we're doing. The client doesn't know what they want yet. They want higher quality, shorter program, safer delivery with cost savings. And alongside Victor Boy, that's just open too, where we prefabricated the whole span off-site, lifted in with shear leg, and it's been a resounding success. What's all these stories got to do in our water bridge? Well, all those experiences and relationships learned, like Dad's Army, have come together to make it a possibility. A lot of the entities have changed, but the relationships have been the same people. Altamana, our bridge fabricator, Demaco, who we used in Govan Partick, will be our moving partner. Sarns agreed to go exclusive with us, which took a hell of a bit of negotiation over in Belgium. And Kudu then our specialist temporary works erection engineers who worked on the pylon erection in Sunderland. We have been able to optimize our fixed span installation from 11 splices down to 2. And their bridge sections are ranging from a 97 metre long pylon with 870 tonne down to an 82 metre deck section at 600 tonne. Our bascule span, we're going to try to prefabricate the whole thing in one piece in Belgium, machine it and position in final support conditions, and transport it as an 1800 tonne 70 metre long bridge section, 40 metre high pylons, and install it in one piece. The lessons learned in Great Yarmouth allowed us to be a bit cheeky through our tender proposals and hang a cart in front of our client, and that we like what you're doing there, but we think we can do a little bit better. And you can see here, in particular, the front wall and the lower clevis, and the incorporation, like Great Yarmouth, between the temporary and permanent works. Now, like Simon mentioned, none of these two schemes is the same, and the ground conditions are completely different in our water. You have the mountains everywhere. You have very hard limestone at 100 MPa within 5 metres, where Great Yarmouth you had 25 metres of Norwich crags and high basal heave issues. So completely different piling methodology, but the same approach. That has allowed us then to also pull in our lower clevis, and we also said, well, why don't we stick a roof on top of that counterweight? There was large tail locks at the back, and that removed a lot of the live load off that back span, which is right a more durable structure, which also doesn't empty its guts into the bascule chamber every time it opens. The saving alone on the piled cover dam is 52 piles, and our competition, I think, it's 6 wheelings to get down to minus 12. We've got 1 wheel at minus 1.5. And again, that's because we went with a Ricky pile method, full of concrete, nice stiff pile wall, where they were going with sheets and multiple frames you have to work through. We've saved in carbon. We've optimized the complex front wall geometry. We're incorporating temporary and permanent work, so you're spending that carbon once on cost. Program savings, and ultimately that was the massive structure which was ground bearing originally, and now we've got a ring of steel and rock sockets. We now have stiffened up that structure, and we're currently working through detailed design, Paul, on the knock-on effects in terms of the bascule. This is our tender model of it opening. So as you can see, complex front wall, tail locks, which is holding up that back span, which was taking those traffic loads originally. So it came back after we won the job to pull that thread, and I think it's been beneficial for all parties, and we're still reaping those rewards at the minute, but with a few challenges to get over yet. What made that possible? That interdisciplinary coordination and the respect of each other. We had a very tight team who worked with each other previously, and we have the capabilities to machine a J-beam on a 1800 ton bridge in situ on site. And if we didn't have that capability, we wouldn't be able to do it that way. And again, that's being respectful of the team around you, getting the right people around you, and investing in the project and getting the end goal. And there's wins and losses along the way, but ultimately we're all seem to be winning at the minute. Without further ado, this is where we've got to. This was our quality submission, if you like, and This has been sped up 3 times, so it looks like we're madmen driving too fast, but lovely piece of music for it, but it's 10 minutes long, so I can't afford it at the minute. This is our deck section 1. Having won the job, we actually opened the book again and said, let's have one more bite of the cherry here. Can we make this better? So what you can see here now is deck 1, which was originally 870 ton with the boot and the stem of the pylon connected. There was a reason for us going that way originally, but having had issues completing the welds on Sunderland with a 90-meter pylon in the air blowing in the wind, we have since decided to move that location, and I'll show you in a minute where that's at. Right, deck section 1, deck section 2. As I said, it's about 800 meters upstream from a deep river port, but we've 0 water at low water, and we've loads of water at high water, and we were very sensitive to, well, we couldn't do a temporary dredge. So in Sunderland, we were allowed to do a temporary dredge, so we could sit there for 3 weeks with a pylon floating on the barge, ballasted. We couldn't do that here, so we did a drone survey and a bathy survey and aligned them as part of the tender to de-risk this transportation method. We've also tweaked our pylon delivery in that we're going to rotate that in the barge and slide it in, because the rotation on the barge has a significant cut, which was possible, but probably more disruption than we needed. Deck section 1 then comes in, and our temporary skid track again was reliant on Saren's expertise and their inventory. So we have the guts of £7 million of temporary works for this, but a lot of that is stuff that is on the market from Saren's, and pushing the boundaries of what they can do, it's fair to say, but getting the right people in the room and challenging what we can and cannot do is the essence of delivering these schemes. As I say, 1 deck splice, so 1 tent, 1 bit of blasting, welding, painting. Finish is applied before we come. Our pylon erection, with a lot of debate over how we do this. You can see there's a hinge. The hinge allows us to use half the size of crane that we need to do the lift by itself. That's a 100-meter stick, and we have since moved this hinge down onto the bottom of the abutment so that this pylon can come in one piece. That has moved that splice from an 80mm plate down to a 30mm plate, which is PT'd onto the base, so it's not going to be vibrating the whole time and cracking your weld as you try and complete it. Our temporary tower, we have changed the form of that and again found betterment. And a lot of that's down to the legacy of keeping the people involved in the tender and the delivery. So then decisions that you can stand over and challenge, you're not getting defensive with your old decisions. It's a 30-mile-an-hour road. I don't know if we're going to get caught or not with speed cameras, but again, that's been fully laser scanned and clash detected. There are numerous streetlights to take down, but it's only streetlights. And drop it down on temporary supports, move the SPMTs to the outside, drive it over the abutment and drop it onto the flat track. So we'll get down to within 50 mil of that, then use a balanced jack system then to slow that down onto the track and tread and hopefully not do any damage, Paul. And I had to cut it short, but that's all I've got to talk about. The one thing I would say is credit to this madman on the left-hand side here, Jim Boylan, who leads a band of merry retirees who are twisted from both sides of the community, who wouldn't take no for an answer and have campaigned for successful governments to make this thing a reality. So without them, we probably wouldn't be where we're at today. So thank you for your time.
Slides there. Used to have questions.
All right, let me just. Does anyone know how to see notes?
No, Ezra, you. See, no, so I don't think so. Sorry, Ezra.
I'm going to freestyle it then.
Yeah.
Okay, cool.
It's my bad.
Um,
No, Ezra.
No, that's cool. Yeah, so thanks for having me. I'm Ezra Groskin from Moxon Architects. It was really great honor to be invited to the Henderson Colloquium and then again to come here tonight. And it was just such good company there to be surrounded by people who all love moving bridges. And I was really proud to have worked with so many of them in the past and working with them currently and in the future. And it was also nice, there were 4 of us architects there, so we were well represented. So this talk is really just a bit of an overview of some different work that I've done and that my practice has done, talking about the role of the architect, kind of design team collaboration, not really going into kind of client and contractor collaboration as well, and just kind of highlighting some various themes and hopefully showing you some nice designs too. So I think as a starting point, it's like, what can an architect bring to this world of moving bridges? It's a highly technical field. As Simon kind of highlighted some of the technical aspects of it that don't even apply to static bridges. So I think the architect's role, I think we see kind of the power of bridges in general, and then the power of moving bridges is just really exciting from a kind of cultural, urban perspective. We're very much into the drama and the excitement of moving bridges and how, kind of getting communities involved and things like that. I think the other thing we bring to it is the way architects are kind of trained to look at kind of bigger problems, not so much silo-based work, but kind of keeping an eye on the overall project, often kind of excited about the power of design to solve problems, often taking on, never saying no to a challenge. Sometimes it gets us in trouble, but oftentimes it serves us well. So a little bit about myself. I was educated at a time when kind of functional modernism was still the thing. Designs were done for a good reason. Bricks were asked, what does a brick want to do? And therefore the brick does what it wants to do, that kind of thing. And then kind of fast forward coming to London, getting involved in a bridge team was a really satisfying way to kind of explore the things that were important to me. So this is the first project I worked on from competition through completion, which is the Bockenhafen-Brücke, which is a bridge in Germany that I was lucky to do with Simon. The bridge, it's a pair of balanced cantilevers. It's one of those structures where the form of the structure demonstrates how it's behaving structurally. So you have a lot of depth over the supports, tapers out in the middle. And then the architects, kind of the games we were looking at is how do you really emphasize that, kind of make the most of that structural behavior. So for us, it was playing with these kind of generous footpaths along the side. So it's quite satisfying and works quite well. And then kind of added on top of that, there's this layer that the central bit is removable, which then you're like, oh, okay, then that structure really starts to make sense. So these balanced cantilevers have this bit in the middle that can lift out. It's a lift out section. Technically it's a movable bridge, but it only gets, I think it's been lifted out once, and it's almost 20 years old, probably by now, over 10 years old. So it doesn't happen often, but it can happen. And because of this, it was decided, or we kind of convinced the client that we could do it purely based on tidal power and ballast. So it's a barge with trestles, comes in at the right time of day, at the right tide, and it's just the power of the tide that lifts it lifts it up, and then it can move it away. So I learned a lot on this project from working closely with Simon and his team. I learned a lot about detailing, and I learned a lot about kind of how much design is too much design. And I think in this one, there's really complicated geometry, And in some places, it's really working and serving a purpose, but maybe in places it went a little bit over the top. I remember this edge detail was just really complicated, and we managed it, and it's built, and we did it, but at times we probably pushed it too far. But one of the things that is quite cool is the way the lift out span is kind of keystone shaped, which means when it's dropping into position, it kind of naturally guides itself to where it wants to be. But then the other thing that's quite cool is as it lifts up, it very quickly clears itself from jamming on the other bit. So lessons like that were really exciting to learn from Simon and his team. So I think kind of the takeaway from that is design should solve more problems than it creates. And that's something that I'm always asking myself and people in the office. You don't do something just because you can do it. Do it for a good reason and see how many problems you can solve at the same time. This is Greenwich Reach Swing Bridge, which is by my office, but it predates my time, but it's just a really good example of an urban moving bridge. I think a lot of times in the colloquium, we talked about moving bridges as machines. They're a great example of a complex machine, but we also like to think of them as objects, bridges in general, but especially these moving bridges as objects within a setting. And I think this is a really nice example of one. It's a contained structure. It's a stayed bridge with a backstay and a counterweight. And you could kind of look at this, and if you didn't spot the bright yellow slew bearing, you might think it kind of makes sense in itself. Maybe there's a good reason to put all the weight on one side of the river and kind of lean out and barely touch down on the other side. But then as it turns, again, the kind of game is revealed, and it starts to make a lot more sense. So for us, designing is looking at this object within its setting. It's also making sure all the different components kind of work together as a cohesive design. So understanding, street furniture, parapets, how do you deal with stay terminations, all these things coming together to create one nice design. In this case, also looking at just the shaping of the structure and how you could integrate the backspan, the counterweight, the stay anchorages, all of this into one design rather than a kind of assembly of pieces. This bit I did a little bit. This was a competition our office was involved in ages ago, and it was one of those ideas competitions looking at Thames crossings. And actually, Tom and other people know more about this and spoke better about it. But I just kept it in as just talking about the power of moving bridges, and also the power of bridges working as networks. So in this case, it's comparing all the bridges in West London to the lack of bridges in East London. And it seems like every, 5 or 10 years, people get excited about the idea of a new crossing in East London, and everyone gets excited and puts all their hope into it. And they think, could this really solve a lot of problems? And then for whatever reason, it doesn't happen. We're all a little bit disappointed. And I think maybe at times we're putting too much emphasis on a single bridge, and maybe there's a dream that someday it's a series of bridges working together as a system. So looking at cities like Chicago, where you have lots of opening bridges and they're all controlled, and you could have smart signage that tells people which bridge is open at which time, and it wouldn't create as much disruption. So this was just looking at that. I think the other thing is the idea of, rather than big openings, small openings, but really controlling how boats move through them. Architects like to talk about competitions. Some of them see them as a waste of time. I think we're quite positive about competitions. I think it's always a good opportunity to develop design, but also develop relationships with other like-minded people that you want to work with. Kind of open competitions, I'm finding that sometimes as more experienced competitors, we can at times handicap ourselves and almost overthink the problem. So it's nice. It's a good thing to stay involved with. We're currently working on a couple of them, and they're all, you always learn something, and you kind of have to go into it with that mindset. So this was a little competition we did ages ago. I think it did get like a really basic bridge did get built here, but it was this concept of a bridge that looks like it's spanning further than it actually is, just through some play with form. But then also looking at how you could kind of conceal an opening mechanism within the form itself. So space for rams and a way that it would support itself in the closed position. Then I moved on to talking about this design collaboration, and I compared it to dance, and the collaboration that we're used to is between engineer and architect. Oftentimes it's really good, and when it's good, it's really good, and when it's times it's not so good, and it's like you're stepping on your dance partner's feet, and you can't wait for the music to be over. But then when moving bridges, in moving bridges, you bring in a third partner, which is this mechanical engineer. And I've been lucky to work with Mike on a lot of these projects. And I think at that point, and there's other, mechanical engineers that we want to be working with as well. But once you get that kind of triangle of collaboration, things can get quite exciting. This is the Royal Victoria Dock, which Simon's already presented, but I just wanted to go through. It's quite a peculiar and distinct design, and understanding how we got there, a little bit more about how we got there. And the way we got there is by the three of us from day one, kind of working on Simon's blank sheet of paper and really figuring it out, all at kind of bid stage or kind of tender stage. So crosses the dock, crosses it diagonal. There's some key axes it's trying to pick up on. There's also some exclusion zones that we're not meant to go into. And then kind of the big constraint is this strip down the middle that needs to be openable for the ship on the top left to get out one day, and for other kind of tallish boats to go through. So obviously the starting point is a straight line, but we quickly realized that made the opening section longer than it needed to be. And as the kind of more expensive, harder to design part of the bridge, it didn't make a lot of sense to make that as long as it was going to be. It also doesn't respond to the axes at the end, and it goes through an exclusion zone. So we brainstormed all the different ways we thought you could get across the dock. So in some, you gently curving. This one, I think, is probably even worse in terms of the length of the opening span, but at least the approaches line up with where they want to. This is getting better, so it's crossing the opening bit is getting shorter, but it's a lot of wiggling. Similar, you're spending a lot of time over the water. This one's quite tight to the existing bridge, the high-level bridge, which will stay, and then you do a lot of work on the south. And then we started getting to these ones where you're crossing more perpendicular, you're doing some wiggling. This one is kind of the compromise where you're crossing nearly perpendicular, you're wiggling, but you're not actually wiggling that much. And we did the math, and it doesn't actually add that much length to the design. So that's the form, and that's some of the reasoning behind it. And then when you combine the way it opens is when it starts to get really interesting. And this is, Simon's already shown it, but it's this using a kind of tried and tested bascule, all kind of the normal components you would want to use, the same types of pivots, but just by orienting the axis along the approach and then having the opening span curve, you get this really dynamic effect when it opens. The other thing is this three-way collaboration. We're all kind of equally obsessed with the details and the kind of machine nature of these components. And this one bit where our disciplines all come together, where the design all comes together, is quite a fun part of the project. And it's something that we spent a lot of time working on and refining and sharing models. And it's yeah, it's quite a satisfying part of the project that will be great one day. So there's just some more images. Going back to competitions, this is just, rough sketching these ideas. And this was before Royal Victoria Dock, but it was looking at, moving pivots so they're not how you expect them and how that affects the geometry when it's opening and closing. Getting a bit of excitement and a bit of, playing with geometry. And that leads to, this is the final bridge I'm going to talk about, which is the Spar Bridge in Dublin. Moving bridge. It's this at the colloquium, this was quite good because there were other projects talking about this stretch of water where you've got a lot of opening bridges and a lot of future opening bridges. So this is one of a series of bridges that are all being proposed for the eastern end, kind of the furthest end of the river where it opens up on to the open water. So you've got a lot of, it's right in the port. It's connecting two halves of the port. You've got a lot of port traffic. And the idea of this bridge is taking that port traffic off the road network and giving it its own designated bridge. It's also providing cyclist pedestrian links for workers within the port, but also for the wider area. So the client here wanted, they came to the table asking for a gateway. They wanted something that could open frequently, but also had a presence within their setup. It's kind of a gateway for river traffic, but also a gateway for their trucks and cars going across it. We are quite constrained. The kind of vertical alignment of the road meant we didn't have a lot of space to play with between kind of the highest tides and the roadway. There's a bridge right next to it, which is another bascule where the counterweight goes down into a chamber. We looked at that and it was a little bit challenging. So we've come up with kind of a slightly unusual situation where we're looking at kind of Dutch bascules and other types of bascule bridges. And just by starting to play around with pivot points, which is something with like Mike's guidance, we get really into understanding the kind of efficiency of these structures. But we came up with this idea that if you could separate out the pivot point of the opening span and the counterweight, you could position the counterweight such that it's at a more effective angle when it's at the beginning of the lift. And you could also take advantage of this pier. We were given a kind of width of pier that matched the other bridge. So pushing the two pivots to either side of that gave us this kind of more efficient structure, but also a much more interesting opening sequence. The other thing, and Paul mentioned this, but the colleague at Covey who we're working with on this, we did a big study into kind of the energy put into counterweight versus the energy required just to lift this bridge. And if you're optimistic about the direction that energy's becoming more and more green in the future, it was actually a really tight comparison between just scrapping the counterweight completely, just pushing it with pure muscle, and over time, you'd actually spend less carbon on the energy than you would invest in this counterweight. The client really wanted a counterweight. They wanted something up in the air, so we've gone in that direction. And I think the other thing we're pushing is that's assuming your counterweight is steel or concrete. But if the counterweight could be a low carbon material such as natural stone, I think that also helps the case for going counterweight. But that was a really interesting bit of work, which hopefully is going to be developed more in the future. The other thing that the client and the design team were kind of pushing from the very beginning is how this bridge, again, it's an object within an urban environment, but how it relates to the other kind of hardworking dock infrastructure in the area. So it's clearly similar in the way it's formed. And then it also is one of a series of opening bridges, a series of really quite important bridges along the river, and the role it will play in that. Hopefully, yeah, so these are just some animations that give you this idea. It's much easier to understand when you see it moving, but you can see this idea of the two pins and the counterweight. It's quite nice to use, we're using these models, as all of us in this room are probably doing, but you're using these as design tools, not just as like a presentation at the end of the day, but as to kind of help you get your head around this complex geometry and interfaces. There's a really lovely bit that I quite like, which is right here, which is this passive lock. It's using the geometry to create this lock so that if the cables were to fail, it would naturally stop itself from slamming down and crushing a car. But as soon as it starts to move, the lock just passively moves out of the way, so it's not preventing movement. So it's just this idea of, yeah, making the most out of geometry and design. There's like one more, and these are sped up. So I think that's it for me. Yeah, so thank you. Hopefully that wasn't too much all at once, but yeah, thanks for having me.
Wow, I just wanted to thank the panelists for coming today and making some like really extraordinary presentations on all aspects of the work in moving bridges. Again, I come at it from a design perspective, but we need to learn from each other, the engineer, the contractor, the architect, and the client. Actually, we had hoped to hear from Christopher Miles of TfL today on the procurement of the Rotherhithe to Canary Wharf Bridge, but he wasn't able to make it today. But I think you can see that it needs us all to be coordinated together to make these beautiful structures. I just want to talk now about kind of where next, really, like what came of those discussions that we all had. And what do we want to do now, really? My experience in moving bridges is actually in the United States, and so I come at sort of my design practice from that history with AASHTO for highway design structures and ARIMA for movable bridges on the railway network. And I'm learning now that we have a series of Euro codes and national annexes, and we also have like a raft of sort of complementary standards here in the UK and in Europe. So there's kind of a smorgasbord of codes, and I think that's what came up from a design perspective, is that there really needs to be kind of a look at potentially a harmonization of those codes nationally in the UK and in Europe, and potentially bringing in some of the expertise in the United States. Ryan was also talking sort of clearly about some of the failures in procurement, right? Bringing together the client with the contractor and the designer, and sort of harmonizing that process so that we can procure our structures in a more organized way. Sometimes they can lead to issues because the wrong people are in the wrong positions and they're not communicating well. From a design perspective, again, going back to those codes, our structures, our moving structures, are really susceptible, temperature movements and the control of those temperature movements kind of within the understanding of those temperature movements within the machinery is quite critical. And if I go back in my career, the sort of the level of complexity of understanding even just 20 years ago is not what we're capable of now, which is what Simon's been talking about. And we see that there needs to be more research in that area, particularly because we do see in our moving structures, especially in hot temperatures, the sort of locking up of those structures. I spent a lot of time in New York, and as temperatures increase, it's happening more frequently. We have to send the fire departments out to our structures to cool them down, to get them operational. And I think that comes from that sort of poor understanding of the temperature effects on structures and the machinery, the binding of those structures. So with all the things that we know we need to improve on, that decision was made to bring together some of that expertise in an IABSE task group on moving bridges. And so that's been initiated, the idea of having one of those. And some of the things that we want to talk about, I've just gone through some of them, but procurement, as I've just said, mechanical design guidance, which again is taken from various standards that they're all complementary. Structural design guidance, particularly around temperatures. Moving bridges, taking into account trains and trams, and this kind of speaks to again the sort of potential for bringing our structures into that sort of net zero environment, focusing on mass transit and bringing that into moving bridge design. Maintenance, looking at how to improve our detailing to make maintenance of these complex elements easier, improving access to those elements, making the machinery more easily replaceable, more easily upgradable, and then accommodating CE marking within that. So the idea is to bring the engineering community together within this IABSE group, and then maybe have subcommittees within that to take the challenge of these items and move the practice of movable bridge engineering forward and improve it. So at this point, I think what we want to try to do is open up to any questions that anybody might have had in the room to any of the presenters, and then maybe open up to a more general discussion about how we can move forward within the framework of improving practice.
Unfortunately, we're running out of time, so it has to be a relatively quick question and answer session. But if the panel want to come up to the front, I'll give microphones out, and then we can perhaps, request any questions. Come on. Right. Okay. Does anyone have any questions for the panel or for Paul? Yes.
So, interesting one about the temperatures. Did you do some? I presume you did a lot of correlation with the codified methodology versus what I class black box methodology, where we're now relying more and more on coding and clever analysis techniques. So, for my understanding, there's more that could go wrong with that reliance. So really, we do need to try to come up with some sort of codified methodology that gives you the robustness and robustness skill as well. Engineering judgment. I like that statement at the bottom end. So how did you feel with the correlation?
Well, I mean, normally I'd be the first to say you don't do 10,000 load cases. Think about how the structure is going to behave and design for the ones that are obviously going to be the most critical. But what we found through this work is that sometimes the behavior of the structure is counterintuitive. I mean, some of the you can post-rationalize, oh yes, that is doing that, but you wouldn't necessarily have thought of it prior to seeing how this work turns out. And again, this is not replacing the rules of thumb and the standards and everything. This is to supplement it. So there were, I think, that we did correlate it, but I think that the biggest difference was the lateral behavior of these structures, particularly because of their plan curvature. When you strictly apply the standards, if you just heat one side of the bridge up relative to the other side, it behaves completely differently to if you just apply a sort of pattern load, which came out of the shading study. So I think that's the difference. But yeah, it's just. What would be interesting is to run lots of cases and then derive some rules from all of that analytical work, because whilst we have the power to do this, it's not always going to be practical to do it, particularly on smaller projects.
Thank you. Any other questions for the panelists? Yes, Tom.
I think about Thames, perhaps. Talk about the client, the engineer, the architect. What about the river authority? Do you think they need to be part of a conversation too? And then do you think, what role is there to sort of work with them on refining their standards, which in a world of climate change and you start to look increasingly kind of gold-plated?
Yeah, I think that's a good point. I think, you know, you kind of ask these people in isolation what they want, and then you just take that as a given. But really, yeah, it just stacks up, and it's actually quite unreasonable at times. And if you can challenge them and really get to the bottom of what they're trying to want, I think we're better off. And that, you know, a lot of times we are talking about challenging standards, and especially given climate and limited resources. I think hopefully that's the direction we're all going. But yeah, they need to be brought on and at times educated or you know, back and forth. But yeah.
Yeah, I was just going to say that's sometimes one of the disadvantages of a design competition, because you get a brief which has been written in consultation with all the authorities, and there's no room for negotiation. If they realise what the implications of some of the things they're asking for are, perhaps they will be prepared to relax them. So you don't have that dialogue.
I guess also opening times in particular, and the impact of 15 seconds and what that has in moving a 1,000-ton piece of bridge at both at Yarmouth and Galway. That was clear. They both opened fairly quick.
It's one of the things we're hoping to draw out in this task group that we're pulling together is sharing that knowledge more widely and more openly. I know currently it sits within relatively few experts within the field, but there's internationally there are differences in views around opening times and safety and various aspects of moving bridge design that's not codified. I don't think it should be codified, but this task group is hoping to bring together some design guidance in the form of a structural engineering document, which is what IABSE produce on moving bridges. So watch this space. It'll be a large piece of work, but we can hopefully draw it out. Be interested to think, you know, based on what we've been talking about this evening, whether anyone has any different experiences in this, or whether you want to contribute something to this discussion on moving bridges. Is there something you feel like we're missing in the way that we talk about these schemes? They're incredibly complicated, but they're very enjoyable to be involved in. No, we've got it covered. Good. Any other questions for the panel or further points that you want to raise?
You have a discussion of a fixed versus movable bridge and how how many different aspects do you need to look at? You know, disruption, the example of the dock bridge, you've got a fixed bridge next to the new bridge that you're building that have a significant benefit over.
Do you want to take that, Ezra, or is it Simon a question?
In the case of the Silvertown Bridge, that existing structure, unfortunately, is an incredible piece of engineering and construction, but unfortunately, it's 3 or 4 stories up, and the lifts never work. We've been on site and we've seen people with pushchairs struggling up the staircases, and our client is building a development with thousands of new homes, and our bridge will provide a direct link across the dock to Custom House Station, so people can get straight into London. And it's unlikely to have to open very often because, well, currently the dock isn't used for an awful lot of vessel movements. Cool. In the future, maybe more, but at the moment, it makes a lot of sense to have a much more direct, user-friendly route for pedestrians and cyclists across the dock.
My understanding is that the LDS scheme for the original high-level crossing had a transporter car underneath it. Did you give any thought to putting the transporter car on rather than putting a new bridge in? No. It would have been a lovely scheme.
That was actually one of the presentations too that Sean Harrington made about the impact to move or not to move, was his presentation in Dublin, and the transformational impact whether you move or open a bridge has had in the narrative around Dublin as it's moved east. And it's always a decision because there's obviously a cost impact when you want to move the bridge or not. And it's whether you want the drama and the cost associated with it, or you want to close up a bit of your river.
And the discussion in London, which Tom alluded to, is how much of the Thames do you restrict shipping from? Where does the Port of London end and the River Thames start? And the decision currently is, well, it's above Tower Bridge. Is that realistic with modern shipping? That's the long-term question for the east of London. Great. Well, unless there are any further questions or points, thank you very much to the panelists and Paul and Giacomo for organising this evening. And as I say, thank you to Ara. But let's give the panelists and their contributions another round of applause. And yes, do come along to the Milne Medal lecture on the 14th of November. We look forward to seeing you there. Thank you.